Well, good morning, good afternoon, good evening. Welcome back to 18th class of this course, and I hope you're enjoying it. All right, so in case you're taking this course for credit, you should, in addition to solving homeworks, you should also give a short presentation in the last class. Here is a tentative list of topics and some instructions. So let me just say a few words about that. So each presentation should be 25 minutes long, and 25 minutes means 25 minutes. So I'm going to interrupt you after 25 minutes. You see, one of the ideas is that this should be a preparation for giving talks at conferences, and some chairs in conferences are quite militant about interrupting you once your time is up. So it's important still to practice to give a talk which lasts exactly for the length of your allotted time. And I here mentioned two standard references for giving talks. One of them is from the 70s by Paul Halmosh called How to Talk Mathematics. It is great, but it is obsolete now largely because Halmosh talks about using chalk and blackboard. And I'm quite sure that at the day when some of the students will have never seen chalk or blackboard in their lives is quite close, especially with Zoom. But still, it contains some very useful advice about structuring the talk, preparing, and things like that. Although, again, he's adamantly against slides. And for 25-minute talk, it is not easy to pull out talk without slides, although far from impossible. Anyway, there is also a newer paper by Bruna Kra from 2013, which also contains a lot of useful and more up-to-date advice. I guess we are still waiting for a paper about how to give a Zoom talk, unless there may be one for all I know. I'm not aware. Now the topics themselves. They're quite varied, both in the subject matter and in the scope. Some of them are very precise, some of them are very vague. Quite a few of them are perhaps impossible to cover in a short talk. But then, what does impossible mean? I think it's second Arthur Clarke's law, which says that if an elderly scientist says that something is impossible, then it is probably possible. Okay, mathematics is not a science, but still, that's the same thing applies to mathematics. Anyways, so please take a look at the list of topics. If something catches your fancy, let me know before somebody else lets me know. And I'll be happy to talk to anybody who is thinking about choosing topic, but they're not sure. If you want, we can schedule a Zoom meeting and discuss what is the most reasonable choice. Probably the most reasonable choice is something that has some relation to research that you're doing anyway. And these massive cyst algebras are connected to quite a few topics. I just realized there is a shortage of topics from pure set theory here. Actually, I see only one that can be interpreted as 100% set theory. So if somebody wants to give more set theoretic representation, presentation, please let me know. We can talk about it, and I'm quite sure that we can find something. All right, so I posted this to the course homepage. Oh yes, talking about posting, you see here, number 14 used to say and their ultra powers, but it is not about ultra powers of cyst algebras with approximate linear flip. It is about ultra powers which tensorially absorb those cyst algebras. So it was easier to just erase the word there and leave it slightly less precise, but correct. And also talking about correcting, exercise number 4 from the third problem set was just wrong. Thanks to Luciano for pointing it out. So I changed it. So in case you spent some time on it and went nowhere, or if you find counterexample that counts as a solution, of course. Anyway, so without further ado, let's go back to the course. And right, so we are still proving that OC implies all automorphisms of Calculus algebra are inner. And last time at the very end, I started, basically I spent maybe less than 10 minutes sketching a proof of a lemma. Since lemma is very important, I'm going to do it slowly now. Basically, I only sketched the beginning of the proof anyway. So we'll see the end of the proof now, but of course I need to remind you what is going on. So here we have this definition of function, which is of product type, but probably first, just in case you forgot, I should remind you what is D. So it is product of D of n's, where D of n is a subset of algebra of n by n matrices, or rather of the unit pole of it, and it is finite, and 2 to minus 1, 2 to minus n dense in this compact metric space. So on the left-hand side, we have some sort of a Cantor space, and the function from that into unit ball of B of H is of product type. If there is function from each D of n into some corner of B of H, and those corners are required to be orthogonal, so there is no interaction between them, and theta, the image of any A, is obtained as sum of images of ANs. Here, A is equal to the sequence of ANs, so each AN belongs to the N. So you just map each coordinate separately, and then at the end put them together, and that's the image. This series here is strongly convergent automatically because those projections are orthogonal and because everything goes into the unit ball. All right, so this is what it means to be of product type. And here is the lemma that I sketched, whose proof I sketched last time. If phi has a continuous lifting theta on some d of E, then it has a lifting of product type on dx of E for some infinite x subset of n. Now, maybe I should remind you, dx of E is product over n in x of those d of n's. So we go to subproduct, and remember, we think of this not only as a quotient, but also as a subspace of d of E, because in each coordinate we have 0, and we just think of elements of dx of E as those elements who support the subset of x, and outside of x they are equal to 0. Right. Now, the part of the proof that we went over last time was finding these stabilizers. So let me here say, so S of J is called a stabilizer. So this is terminology due to Winfried used, but the idea really goes back to Sakharov Shelach and to his proof that I'm going to discuss a little bit later on. So what these formulas mean is that if you look at our indices, here is n of j. If you take just a second. Right, so here is n of j, here is n of j plus 1. Now a and b are here. They're perhaps anything. C and D are here. They're again arbitrary. So this, I just mean the product of the n's. And here we have just s. If you compute theta at different combinations of a, s, I mean of something from here, s, and something from here, then in this interval between then changing what comes before doesn't change what comes after Rj, and changing what comes after doesn't change what comes before R sub j. Right. So essentially, all elements of the product that go through this S are stabilized. Are stabilized at this very place. Okay, so now from here we want to construct lifting, which is of product type. And so first we take a look at this set X, which is set of those of exactly those n of j's. Right, so this is a very thin subset of the natural numbers. And now S is sum of these S of j's. Now S, let me see, S of j is here. This is support of elements of dx, and sj's are disjoint. S of j's are just interspersed between elements of x. And S is the sum of all of those. And now for each j, define this theta tilde j, which maps dnj into this corner here between rj and rj plus 1 of b of h, unit ball of b of h. Remember, rj's are approximate unit consisting of projections for b of h. And theta j prime of x is, how do you compute it? Sorry, this is xi. Xi j tilde of x is theta of s plus x, which is compressed by rj plus 1 minus rj on both sides. Now, the point here is that the fact that you're going through S doesn't make much difference here, and the salient property of theta j of x is the following. If you look at theta j tilde of x minus theta of x, rather theta of x plus s, if you multiply this by rj plus 1 minus rj on both sides. Okay, I have to move this a little bit, right? So if you multiply it by both sides, on both sides by this, what you get is less than, let's see, so it will be 2 to minus j plus 1, I think, because you have errors on both sides. But basically, j goes to infinity, 2 to minus j plus 1 goes to 0. So theta j tilde of x is just like theta of x plus s, at least on this window between rj and rj plus 1. All right, so you see, if you take this function that sends x to sum over j in x of theta tilde of j of x n of j, it is a functional product type, right? It is by definition, but it's probably not a lifting. And the reason for why it is not a lifting is that, actually I didn't call this function anything. Let's call this theta tilde, sorry, xi. Why am I saying theta? Xi. Xi tilde. Xi tilde of s minus theta of x plus s. Oops. Yeah, this is a place where you should not be writing. Okay, let me move this. All right. So this is a compact operator for every x. Right, so basically the issue is that this stabilizer that helped us make something sensible and relevant out of this lifting theta, which was just continuous. We have to get rid of this s if you want to have an actual lifting. All right. So, okay, so it wasn't necessary to take this. Now, what we can do, well, you see, let me just roll back to this formula here. You see, actually, I can probably copy it because I'll need it again. Not cut, I wanted to copy it. Right, so you see what is happening. This xi tilde of x is equal modulo compacts of theta of x plus s. And we don't want that. But okay, that's easy to fix. You can just compress by qx. And again, there is a lot of notation here. Remember, qx is phi star of px, and px is the projection to the closed span of all those xj's, such that j belongs to union over n in x ej. Right, so it's the projection to the sum of the blocks indexed by x. Okay, so this is it, and theta. There is an equality sign missing here. So we can take theta 0 j of x to be this, and theta 0, what? Sorry, I was just deciding right before the class that something should be said better than they're said in the book, and may have messed something up. By the way, I already mentioned this, but the proof I'm doing right now, the proof given in the book was somewhat, well, okay, there were typos in it, and it was also a bit lacking in details. So there is errata, which contains more details. But different details from what I'm doing right now, because I just decided that there is a better way to say all this. Let's hope it's a correct way as well. Let's see, theta 0j is this, and this. Yeah, okay, no. So what I wrote here is silly. So this is of product type by definition, but it's not a lifting. So just scratch this. Okay. So what I wanted to say is take this. Theta 0 of x is qx, is theta tilde. Okay, maybe I shouldn't be using x because x means something else, and it's difficult to see in my handwriting which one is x, which one is capital X. So I'll write it with a little a. So if I don't need s here, oh, sorry, what's here? Okay, so I just compressed this by qx. Now this theta 0 is a lifting, but not of a product type. Right, so it is composition of a lifting of product. Sorry about this, I still have to learn how to press the right page in right moment. So it is a compression or lifting of product type by projection, but the issue here is that Q is probably not commuting, QX is probably not commuting with all of these elements. And because of that, when you multiply by QX, this product type structure gets destroyed. Okay, so and here comes the part where I'm taking departure from what is in the book or in the errata. There, I just painstakingly made sure that I go to a thin enough set on which everything works. But that is not necessary. So you see, what is a fact? Let epsilon j be the following. I take maximum over all little b in d sub nj of the following. We take norm of the commutator of qx and let's see, so what was the notation? Notation was theta tilde j of b. Right, so once again, the issue is that qx doesn't commute with these. Well, okay, so we just measure how badly it doesn't commute with them. And now the point here is the fact that epsilon j converges to 0 as j goes to infinity. Right, so this is the key thing here. So assume not. Otherwise, fix epsilon greater than 0 and y subset of x infinite and bj in dnj for each j and y, which has the property that it witnesses that something goes wrong, right? So the norm of the commutator of qx and theta tilde j of bj is greater or equal than epsilon j. All right. Now let b be the sum of bj's, right? So everything is here strongly convergent, that there are orthogonal elements in the unit ball. So this makes perfect sense. And then what do we have? Well, pxb is equal to bpx, and it's equal to b. Why is that so? Well, okay, equal modulo compact. So I'll just put little dots. Remember, by putting little dot, I mean I'm looking at the image in the calculus algebra. Why is that so? Well, because B has been chosen inside this dx, right? Okay, so what this means is that oh yes, actually, more relevantly, also, if I look at px b plus s, this is equal to b plus s Px, and it's also equal to B, right? For the same reason, S lies in the orthogonal, right? So what that means is that when I apply phi, our star homomorphism, then Qx okay, so let's see how do we write this. So let's say Qx times theta of B plus S. Remember, theta is this continuous lift of phi. So Qx theta B plus S is equal modulo compacts. So I'll just write it minus theta B plus S Qx. This is compact. Okay, but what that means, it means that Qx times this theta tilde of B plus S. Actually, I can just write it this way, that the commutator of this belongs to the compacts, right? And the reason for that is that this and this are equal modulo the compacts. All right, but what is theta tilde of B plus S? Well, it is the sum of these guys here, right? So what that means is that we get a contradiction, right? But let's call this star. So this is contradiction with star. All right. So this proves the claim that this epsilon j. Let's just see epsilon j once again. I'll take advantage of high tech here. Oops, want to leave it there. Copy. Now where am I? Okay, I'm actually here. Good. Right. So it satisfies the epsilon j goes to 0. And now what that means, so choose y subset of x so that sum of those epsilon j's for j in y is finite. Right? And then on dy, this theta 0 of a, if I just hold on, write it in a new formula, in a new line. Theta 0 of a defined by Qx sum j in y, just need to theta tilde j, theta tilde j of aj. This is a and j. Remember, I had this indexing that j in y really means that n of j's are those chosen indices. This times, okay, let, okay. Then, okay, so what do we have? Oh, actually, sorry about this. I'll have to put Q here. So this is of product type by definition. And also for A in dy, theta 0 of A is actually equal to Qx sum j in y theta tilde j A and j Qx, which is equal to, well, equal modulo compacts. Okay, so I'll actually have to use some notation. So by this I mean, let me just use it, write this in a different, equal modulo compacts. And so this is equal to, right, so it's equal to Qx, again, modulo compacts of theta of A plus S Qx, which is equal modulo compacts to theta of A. So it is a lifting. Right, so basically what was missing, why the proof was unnecessarily long, was failure to observe that these norms of these commutators converge to zero. All right, so that was the lemma that we started last time. So what lemma tells us, once again, is that we can go from just a continuous lifting to a lifting of product type at the expense of going to a subset, to infinite subset of the indices. But we'll see that that doesn't matter. Now, before moving on, let's just take a look at historic context here. Where exactly is this proof coming from, and well, where is it going? So basically, I'll talk about the grandfather all of these proofs. Look at automorphisms of the commutative version of the Calkin algebra of L infinity mod C0. And when I just say L infinity mod C0, I mean L infinity of n mod C0 of n. So it's the separable version of C0, and L infinity is also separable. Its unit ball is separable in well, weak star topology. And look at automorphisms of that algebra. The algebra is abelian, so it doesn't have any non-trivial inner automorphisms, but we can talk about trivial automorphisms, and those are the ones that can be lifted to a star homomorphism from L infinity to L infinity. Right, so you know, another way to say this is that really there is a permutation. Well, okay, not permutation. There is a bijection between cofinite subsets of natural numbers corresponding to indices, so that that bijection sends elements to elements of L infinity. And right, so the groundbreaking proof of Sakharov-Shelach from late 70s, I'm not sure that 79 is the exact date, is that this assertion that all automorphisms of L infinity mod C0 are trivial is relatively consistent with ZFC. This proof appears in his book Proper Forcing, and at least according to Winfried Just, it is the most complicated proof in the entire book. I haven't read the entire book, but it is it contains lots of very complicated proofs, and this one is definitely quite complicated. Now, you can see connection between this and assertion about Calkin algebra having only inner automorphisms. Basically, the latter is a non-commutative version of the former with the obvious necessary adjustments. Now, Shelach's proof is application of something called oracle chain condition. It's very intricate forcing iteration. We are not doing anything like that. So really much more closely related to what we are doing is theorem of Ilijas, which proved some 10 years after Shelach, which says that the same axiom that we are using plus so-called Martin's axiom that we'll not need, but it's a very popular set theoretic axiom. I guess second in popularity after continuum hypothesis, probably. So those two axioms together imply that all automorphisms of L infinity mod C0 are trivial. Essentially, what Veličković managed to do is recast Shellac's proof in the language of forcing axioms. And now the reason why I wanted to say a few words about this is that each one of these proofs proceeds in 3 stages. I'm just trying to see where am I. I think I'm here. Yeah. Proceeds in 3 stages. So what are stages? So stage 1 is the following. There are many x subset of n, x infinite, such that phi restricted to L infinity of x modulo C0 of x. And you can think of this as a subalgebra. Basically, just look at the functions which are supported in x. This is trivial. And of course, phi, so fix phi, which is an automorphism of L infinity mod C0. Now, okay, so what exactly does many mean? There is a very precise notion, and we'll be in a similar situation very soon. So basically, if you take uncountably many infinite subsets of natural numbers, so that any two of them are disjoint modulo finite. And we actually constructed something like that, you may remember, several weeks ago. So if you have uncountable such family, slightly more precise than, I mean, specific such family, but basically such a family, then restriction of phi to all but countably many of your sets is going to be trivial. And now, after this, each of these proofs proceeds to show first that the family of such sets is regular in certain way. It forms a p-ideal. Doesn't matter what p-ideal is, but it has certain structure. And third part of the proof is uniformization. And that very closely corresponds to what we did in the beginning of this proof, when you proved that OC implies every coherent family of unitaries is trivial. Closely, it's somewhat different. You're uniformizing from a different side, but basically same idea, and recurring idea in many applications of OCA. Now, it was only natural to expect that proof that all automorphisms of the Calkin algebra are inner would proceed in the same direction. Now, important bit here, you see the first part uses only OCAT, and second part, right, second part really uses Martin's axiom, maybe with OCA, I'm not even sure now. I think you just need Martin's axiom, but I'll just add OCAT. And then third part, again, uses OCA. So basically, it seemed that that proof would have to go that way. And now, indeed, in the case of L infinity mod C0, it is true that just having many subsets of natural numbers on which phi is trivial does not imply that phi is trivial. There are many models of set theory in which some funny things happen. You have automorphisms of L infinity mod C0 which are locally trivial but not quite trivial, and so on. Basically, the point is that in the case of Calkin algebra, that cannot happen. Luckily, the moment we complete analog of stage 1 of this proof, we are done. And that is a little very useful and clever trick. I mean, it's probably hard to say whom is it due because it's actually really easy. But here it is. And now I want to state a version that will not be used in the proof, just because this is the easiest version to state and easiest one to appreciate. We'll have to use some slightly trickier variations on this. All right, so here it is. So suppose that phi is an automorphism of Calkin algebra and P is a projection. Okay, I should say here that P is not zero, right? We don't want a zero projection here. So P is a projection which has the property that restriction of phi to this corner is trivial, which here, of course, means implemented by a unitary, right? So there is a unitary which implements automorphism there. Then all of phi is implemented by a unitary. So in other words, if automorphism is locally trivial in this sense, then it is automatically trivial. One has to be careful here because under continuum hypothesis, we construct an automorphism which is locally trivial in a completely different sense, but non-trivial. So this is basically have entire corner which is isomorphic to Calkin algebra. And as I said, this is very easy to prove. So just fix an isometry being Q of H such that V star V is identity. I'll write 1 Q of H, and V star is equal to P. Why do I have that? Well, H is a separable Hilbert space. I can lift P to a projection in B of H, and that projection has separable range. So all Hilbert spaces, all separable infinite-dimensional Hilbert spaces are isometric, and therefore that isometry is the isometry that you want. Okay, now you see the point here is that V belongs to Q of H. All right, so then, oh yes, also fix this unitary, so fix W such that the function, the conjugation by W, A maps WA. Actually, I can write this in a better way. Fix W so that for every A in this corner, PQ of HP, WA W star is equal to phi of A. All right. Now, what do we have? For A in Q of H, well, I can write A. You see, because V star V is equal to 1, I can write A as V star V A, V star V. I just multiplied it on the left and on the right by the identity. Right, so if I apply phi to both sides, I get that phi of A is equal to phi of all this on the right-hand side, phi of, but okay, I'll split it in this way, phi of V star, phi of VA V star, and phi of V. Now, what about this guy? Well, look, where is VA V star? It belongs here. Why is that so? Well, because, okay, so let's, if I multiply VA star by P, what is P? P is V star. So this is V star VA V star, but this here is V. And similarly, if I multiply by P on the right. Right, so VA V star is in this corner, which means that this is just equal to phi of V star, and phi of VA V star is WAW, not WA, it's W VA V star W star phi of V. Right, so did I? Yep. And now, what do we have? This here, let U be phi of V star WV. Well then, phi of A is UA star. Right, this here is exactly U star. You can see it by conjugating term by term. And moreover, U is a unitary, which basically falls from here, but you can just check it, that U star U is equal to 1, and it's also equal to U star, right? Just basically the fact that W is a unitary and that V is an isometry. Right, so you see this little trick shows us that we don't have to use Martin's axiom, that all that we want is one corner of the Calkin algebra on which automorphism is inner. But as I said, the proof doesn't proceed that way. We have to handle these subalgebras. No, we have to. I mean, that's how the proof goes. Maybe there is a better proof which proves directly that on some corner automorphism is inner, but or implemented by unitary. But I would like to see that proof definitely. All right, so this was just basically instructive for seeing what to look at. Now, this lemma, this is what we just did, has many analogous similar versions, and I'll state a few of them which we'll need. So here is another one. Suppose phi is an automorphism of Calkin algebra, and the restriction of phi to dx of E is implemented by unitary for some E, such that, now this is important, that the lengths of these intervals, these E n's, converge to infinity as n goes to infinity. Then the restriction of phi to d of f is implemented by unitary for every f in part of n. So this is what we want to prove. I'll have to prove a few more things before we come back here, but let me just tell you, why is this important. So you see, in the previous proof, we started from a continuous lifting on this d of e. Oh, by the way, notice different fonts. This here, this is script dxe. So this is subalgebra. This is von Neumann subalgebra. Right, so this is not one of those Cantor sets. This is the entire real McCoy. But okay, we'll go to those in a moment. If restriction is implemented to something like this, then restriction of phi to any d of f for any f in part n is implemented by unitary, which will mean that well, we just do it once. Okay, so let's right, and now there is the next lemma. Okay, which is something that we are not using here, but basically just shows that in case of isomorphism between coronas, completely analogous statement holds with completely analogous proof. Right, so here you just have two coronas of non-unital cyst algebras, and if this isomorphism is lifted by an isometry on some corner, then you can lift it I mean, assuming that this corner is equivalent to the entire algebra, you can lift it to the entire algebra. And also, you see, instead of implemented by unitary as we had in these situations, if you assume, for example, that you have continuous, let's say just continuous lift, then if you remember the proof of this, exactly in the place where we inserted this conjugation by W, WA, W star, we could just put this continuous lift. And then what the proof shows is that the composition of that continuous lift with conjugation by some unitary is a lift. But conjugation by unitary is continuous. So if you have continuous lift on a corner, you have continuous lift on the entire algebra. And the same goes for C measurable. And the same goes for epsilon approximations in place of lifts. Remember, epsilon approximation is something that guesses the image only up to epsilon, even after you mod out the compacts. And the point here, of course, is that isomorphism between C algebras are isometries. So conjugating by unitary doesn't change this epsilon. Well, okay, it's actually conjugation by unitary is an isometry, so it doesn't change epsilon. And the same remark goes to lifting so product type if you set up things correctly, so that it's slightly more subtle here, but basically the same proof every time. So the whole trick is that just like here, if you have this projection, all that you need is this isometry such that V star V is 1 and VV star is P, and that isometry belongs to the algebra, so automorphism sends it somewhere, and out of that somewhere, out of that image, you can reconstruct what you need to lift your map. All right, we go on. So okay, so we go back to our settings. So we have H, which is our separable infinite-dimensional Hilbert space, and orthonormal base is Cj. Now, if I just take an injection G from natural numbers to natural numbers and define this map, so Vg of Ci is Xi sub G of I. So this is mapped from basis to basis, which is injective. I can extend it to a map from H to H, right? So the linear combination of lambda I Gi is just mapped to linear combination of lambda I Xi sub Gi, right? So this is this isometry Vg. And we'll need them. So I have a special name for them, which is actually lousy name. Now that I think of it, injection, I could have, okay. Anyways, so unfortunately, they are named injection isometries. And because they are isometries coming from injections. But of course, isometry is an injection. Anyway, okay. So here is lemma. So basically, we are going towards proof of the lemma that was the middle lemma on the previous slide that I said we want to prove. Suppose E and F are in part n, X and Y are infinite subset of n, and limits of the lengths of intervals En as n approaches to infinity through X is equal to infinity. Then there exists a permutation isometry V such that A goes to VAV star defines an isomorphism from DYF onto VV star DX EVV star. All right. So how do we prove it? Or other question is how not to prove it. So stop me if this is too obvious. Okay, so proof, find, let's call them Mn in Y so that Mn is greater than cardinality of En, and also we want these to be increasing. Right, so this should be true for all n. What? No, sorry. This is not what I wanted to say. Right. I turned it around. Mn is in X, and Mn is greater than cardinality of Fn. All right. Now this is better, right? Because that's what my assumption tells me, that I can do something like this. All right. And now, how do we construct our function? Well, just G. How do you want to define G? Let's just see what direction does it go to. So make sure that okay, pick G. So that G sends Fn into E sub Mn injectively, right? So these elements are getting larger and larger, and then this is G works, right? So that then, except for one thing, this is okay. This is for n in Y. So this is not really permutation isometry. This is permutation partial isometry. Right. So then, if I take VG star VG, it will be PFY. That's why it's a partial isometry and not an isometry. And VG star, well, it is some element of DE. But what matters is that if I look at VG A, VG star, this will belong. Okay, so I just have a problem with notation. So this sends PF. Okay. Well, it does what it's supposed to do. It sends DYF into VG star DX E VG star. Right, because at the level of these finite dimensional blocks, it sends each block of F into some block of E, right? So we are not getting exactly sizes of blocks, but that doesn't matter. Right, so this is our isometry, and now we can just put things together. Any questions? Okay, so this lemma is putting things together. So suppose that E and F are in part, X is subset of N, V is an injection isometry, such that A goes to VAV star defines an isomorphism from D of F onto VV star DX EVV star, exactly like what we produced on the previous slide, except that we had DYF, but y here is assumed to be all natural numbers, and phi is an endomorphism of the Calkin algebra. You see, in many of these lemmas, we don't need to know that phi is an automorphism. Everything works with endomorphism already. So part number one, if restriction of phi to dx is implemented by some w, which is probably unitary, then the restriction of f phi to df is implemented by phi v star wv. And you probably recognize that this is exactly the formula that we had in the previous situation. That's exactly what you obtain by working this out. So basically, we already proved this in a slightly different context, but as I said, all of these proofs are analogous. Second part, if phi has a lifting of product type on dx of e. Now note font has changed, so here we are talking about these Cantor sets, these product spaces. Then it has a lifting of product type on d of f. And
somewhat subtle type. Oh, something happened.
Can you hear me? Yes.
Something happened. It's true, but
yes, something
I can
happened.
hear you now.
Something happened, but you see, these headphones I just love them, but they have this completely idiotic feature that whenever I connect headphones to a device, device starts playing music, and it's impossible. Actually, I think I was saying this last time, right? I'm repeating myself. Anyway, it happened again, so I don't know why this happened, but you can hear me now. Yes. Okay. Good. Right. So talking about the proof of two. You see, important thing is that this V maps blocks to blocks, right? So each block of D of F is mapped into a block of dx of E, which means that when you compose function of product type with conjugation by V, then because conjugation by V is also product type, it doesn't combine blocks, you get something which is of product type. Right, so this is because A goes to VA V star is of a product type. And part three, if theta is a C measurable epsilon approximation, which is actually what we'll be having to deal with of phi on dx of E, then this A goes to phi star of V star theta of VA V star phi star of V is a C measurable epsilon approximation of phi on D of F. Now this is exactly the same formula as before, except that here you don't have conjugation. You're just applying this C measurable epsilon approximation. And the point here is that this A goes to VA V star is C measurable, and it's isometry, right? So if you compose two C measurable maps, what you get is C measurable, and if you compose epsilon approximation with an isometry, you get epsilon approximation. Okay, so again, this is the important situation for us, and we are trudging along, and basically we can now change the gears and introduce one of the key concepts in the proof. Now this is a concept that is very general and doesn't belong to set theory. It hardly belongs to operator algebras. It is basically I guess first person to consider anything like this was, at least as far as I know, was Stanislav Ulam. So this is, we are entering subject called Ulam stability, but let me first state definition and then we'll discuss it. So you're given epsilon greater than 0 and two C-star algebras A and B. And now we have theta, but we just look at restriction of theta to the unit ball. just look at map from unit ball to unit ball. That's all that matters. Everything is homogeneous. And we say that such a theta is an epsilon star homomorphism, or sometimes people say approximate epsilon star homomorphism, if for any pair xy in the unit ball of A1, and for any scalar lambda of absolute value at most 1, we look at the following. We look at theta of x star minus theta of x star. You see, if theta were a star homomorphism, this would be equal. But we just ask that norm of that is not greater than epsilon. Right, so it's epsilon star preserving. And just do that for everything else that makes sense, right? So it's theta is epsilon additive, theta is epsilon multiplicative on the unit ball, right? So this is important if, really we are looking only at elements of norm 1. And finally, also multiplication by scalar. Theta is respects multiplication by scalars up to epsilon, but only as long as everything is in unit ball, including the scalar. And also one technical simplifying assumption, we say that theta is unital if also theta maps unitary group of A into unitary group of B and sends 1 to 1. Now, this last part can always be arranged. If you have an epsilon star homomorphism, even, okay, between unital cyst algebras, of course, you can always perturb it a little bit and assure that this holds, but we just don't want to waste time on perturbing. We just assume it by design. So as I said, it was Stanislav Ulam who first considered this sort of question. And his original question was, if you have an epsilon homomorphism between metric groups, is it necessarily a perturbation of an actual homomorphism between groups? There are many positive results. We'll prove one of them next time. Very nice theorem of Berger, Ozawa, and Tom. But actually, the answer to Ulam's question is negative for very simpler reasons. So here is something. I'll just mention this because I guess it is important to realize that this is not an obvious question. So so here is let's say theorem proved by Vladimir Kanovey and Michael Rieken some 20 years ago, I think. So there is okay, for every epsilon greater than 0, there is an epsilon homomorphism between metric groups. Let's call it F mapping G to H. Okay, let's say G to K because H is Hilbert space. I don't want to, let's say F epsilon G epsilon K epsilon, such that okay, so just when I think that I got this under control, here. Okay, such that one, every homomorphism F from, okay, G epsilon to K epsilon is trivial. I mean, basically, just everything goes into identity. And 2, well, actually, I don't even have to say this. Okay, I don't need to erase this because it's not false, but it's not. It's part of the proof, really, such that the distance from f epsilon to f is at least something like 1/2 for every homomorphism f mapping g epsilon to k epsilon. And the proof just so pick n, which is greater than something like 1/epsilon. And now think of z mod nz as subgroup of the circle with the natural metric for every n, and just take f from z mod nz into z mod n plus 1 of z. So this is f epsilon, such that f epsilon of x minus x is minimal possible for all of these. So it's at most e to 2 pi I divided by n plus 1 for all x, right? So with this, it is very close to the identity, and therefore it is epsilon homomorphism. Okay, maybe I didn't get this right, but basically, and I'll just say n large enough. Don't want to compute algorithms right now. So basically, f epsilon is an almost isometry, but you see there is no non-trivial homomorphism from one group to the other. So basically, this Coulomb stability question is non-trivial. It's a whole subject. I mean, if you just go to Google Scholar and see that there are tons and tons of results, which are often proved just for their own sake, but right now we actually need it for very precise reason that we want to prove a theorem. So these Coulomb stability questions naturally occur when one tries to prove rigidity of quotient structures. And here is our theorem. Suppose that phi is an endomorphism Kalkin algebra, which has a continuous lifting theta on D of E for some E, such that these intervals En, their lines converge to infinity. Then for every f in part n, phi has a lifting theta n prime of product type on D of f. Now note that the font has changed. This is now a von Neumann algebra. Right? You see von Neumann algebra versus just a Cantor space, such that each theta n prime is a unital, well measurable epsilon n star homomorphism on D of f for some sequence converging to 0. Right? So just in case it wasn't clear, so the lifting, it would be more appropriate to say that lifting theta, theta of A is some theta n prime of A n, where here A n belongs to D sub singleton n of f, right? So theta n prime acts on the nth block. Right, so this is just a somewhat unfortunate notation. So by this theta n prime in round brackets, I mean that this is a sequence of maps from finite algebra to finite dimensional algebras, which gives us our lifting. Okay, so what remains to be proved here? We actually did most of the work. So what we proved is that, oh yes, that there is actually one thing that we didn't prove. One thing that we didn't prove. Okay, so first we have a lifting. Okay, let's call it C, and I'll use the same notation. So it's a Cn of product type on D of F. So this is Cantor-like space, right? So this is not a von Neumann algebra yet. Right, so this is what we get from isometry trick. We just choose this isometry from one space to the other, and just because isometry is also product type, if we just conjugate by that isometry, we get lifting of product type on D of F. Now we want to move to von Neumann algebra. Now, oops. Now, on each one of these building blocks, now this is somewhat lousy notation, but I'm just trying to be optimal here. So if I just have singleton n in subscript, it means that this is really the algebra which corresponds to the nth block, to Fn. So just look at span of those indices in the basis in Fn, and just look at that matrix algebra. So on this, let alpha n mapping unit ball, remember only unit ball matrix, maps this into D I think notation was dn of f. So this is this finite set. Be such that alpha n of x minus x is less than 2 to minus any norm, right? I can do this because this set is 2 to minus epsilon dense, and alpha n is Borel measurable. Basically, I'm just sending each x to the first possible candidate, and that's going to be Borel measurable, and pre-images are going to be differences of open sets. Okay, so then actually we proved this before. Then if I look at alpha of x, which is just sum of alpha n of xn, satisfies alpha of x minus x is compact. And because the error at the nth coordinate is 2 to minus 10, they're all orthogonal. So the difference is in the compact operators. Okay, so I can just compose alpha with psi. Right, so let's see. Psi composed with alpha is a lifting of product type on script D of F. Right, so basically I was making fuss over nothing really. Passing from Cantor set to this von Neumann algebra is not a big deal because Cantor set was chosen to be sufficiently dense. So we have lifting of product type on this, but what we need to prove is that these maps are star homomorphism, epsilon star homomorphisms. So this is really our theta. now claim for every epsilon greater than 0, for all but finitely many n, theta n, and theta n is just composition of Cn and alpha n, is an epsilon star homomorphism. Right, so basically I'm claiming that I don't need to do anything, that already the map that I have does the job. And what is the proof? So assume otherwise. All right, so there are only finitely many things that can go wrong. Right, then what did we require from epsilon star homomorphism? That it is epsilon star preserving, that it's epsilon star additive, epsilon multiplicative, and epsilon multiplicative by a scalar. So it's only 4 things. And now, otherwise, if this is not true, then one of those things fails infinitely often. And we just have to check for each one of them. But the proof is the same. So let's say assume otherwise. So assume that there exists epsilon greater than 0, such that there are infinitely many n, such that theta n, okay, I'll just write the whole thing, is not an epsilon star homo. Now, case 1, there are infinitely many n, such that there exists some x in the n of f, such that theta n, actually this is, I got the wrong font, right? So this is von Neumann algebra, but the unipole, such that theta n of x star minus theta n of x star has norm greater than epsilon. And let's call this xn. Well, then what happens? With x equal to sum of these xn's, so I'm taking only some of those xn's and that other coordinate just leaving zeros, we have that theta of x star minus theta of x star, well, this difference is epsilon forever, so this is not a compact operator, but this is a contradiction. Right, because theta is a lift of our star homomorphism. And the other 3 cases, the proofs are analogous. Right, so we are in a situation where we started from just continuous lift, and what we got is lifting of product type, so that even these maps are epsilon homomorphisms for smaller and smaller epsilon. And that basically brings us to the last part. Yeah, okay, so basically this is what we want to prove, but to prove this we'll need to prove Ulam stability. So that comes next time. Right, so definitely if you're trying to see why this follows from what I said, it doesn't. That there is a big part of the proof missing here. So Ulam stability, and there is a question of for what cyst algebras you have Ulam stability. All that we know is that if you have phi from A to B, if A is finite dimensional, then we have stability. Nothing else is known at all. But anyway, I guess I should discuss that next time, especially because my iPad is at 7%. So I guess that's about it. Okay, so that was all for today. Let me know if there are any questions. If not, in case you need to choose presentation, let me know so we can talk about that. And yeah, so it seems that there are no questions. All right. Okay, so stay safe and see you on Monday. All right, bye.